Yeah. Okay, so today we have February the 12th, and we have a lecture on optimization, on constraint optimization with concavity considerations. And let's go. Okay, so I will share my screen. Okay. So just a small check whether you can see everything.
Yes.
Okay, now let me remove this. And okay, let's start. So I will just type some notes when I'm working, so it will be mess for economists. We have 21st year, second month, 12th. Okay, and we have concave, convex functions in optimization. Okay, now I think so. Everything works. You can see what I'm typing. You can use the link and scroll up, scroll down. Everything is fine. Just to check.
Yeah, it works. It works.
Okay. So first, I would like to finish one small topic I forgot about homogeneous functions. It's very simple, but I've left one small point I left about homogeneous functions. And so you will see how I will type mathematics using LaTeX in Colab. Just a small point on homogeneous functions. Okay, I will just move some windows because on homogeneous functions. If we consider a homogeneous function of one variable, then it's very boring. Basically, there are only a few types of homogeneous functions of one variable. So let's prove the following theorem. And the unique homogeneous function of one variable is which one? Who can guess? Which one is the unique homogeneous function of one variable?
Fx equal to x.
Basically, yes. Yeah. Or maybe it's better to write all homogeneous functions, or all homogeneous functions of one variable are of the form f of x is equal to some constant times x to the power k. So basically all homogeneous functions of one variable are of this type. That changes in a multivariate setup, but when we work with function of one variable, then it's very easy. Let's prove it. Let's prove it. Okay, the proof is very simple. We know that our homogeneous function is a function of one variable, and we know it's homogeneous. So basically, we state that f of tx is just t to the power k f of x. It's a condition of homogeneity. And in our case, that should work for every t and x from our domain of the function. And so we can choose basically any x, any t, and that equation should be true. Okay, so let's choose the x equal to 1. So that works is true for all t and all x for which both sides are defined. And then I just, let's choose x equal to 1. And bingo, we get that we obtain that f of t is just t to the power of k times f of 1. But as f of 1 is a constant, so basically we have that it's some constant times t to the power k. And basically the proof is completed. So we see that there are very few homogeneous functions of one variable, and the diversity is in homogeneous functions of many variables. So that's not the case when I consider even two variable cases. That's not true even for two variables case. So in this case, I can provide something like f of x, y is x to the power 5 cosine of x over y plus y to the power 7 divided by x plus y sine of x over y. So I can get something like this.
I'm sorry, can I ask one question?
Yes, yes, that's the main difference between me and a book of by Rangarajan Sundaram or any else.
Yeah, so the theorem says that f of x can be presented in the following way. So it's constant multiplied by x to the power of k. But in your proof, so I mean, x is a variable, but in your proof, t is also a variable, or
yeah.
But I think if we multiply all like all our variables by t, t is has to be constant, no?
But it holds for t equal to 2. It holds for t equal to 5. So just replace by t by a by x. What's the problem? If it's satisfied for all t, so this equation, so this part, the part I have selected is satisfied for all t, for all x when they are defined. That basically means just rename them. It's satisfied not in one point. This is so it's not an equation like only one t will be okay. All t are okay. So for t equal to 1, for t equal to 1.5, for t equal to 1.7, for all x, you get the same equation.
Yeah, this is absolutely clear. But I mean, in terms of initial function, x and t are a bit different things, no?
Oh yeah, so I don't get your point.
Yeah, so that's a bizarre question. Okay, I'm sorry.
My idea is that so if I write Quentors, so it should be is true. So this is true for all, yeah, for all t, yeah, for all t. And if it's true for all t, I can replace t by any other name. I can replace t by k or by x.
Yeah, but f doesn't depend on t initially, no?
But in my last equation, it depends on t.
Ah, okay. So again, I'm sorry. Thank you very much.
So in my first equation, yeah, f depends on x. Okay, so I may maybe if I change here, maybe it would be better to understand f of t is okay, and like that.
Yeah, totally clear. Totally clear. Thank you.
So just the question of naming variables. Okay, let's move on. So we have proven, oh, we can even collapse some sections. Wow. Wow, that's cool. Okay, let's move on. Now let's go back to concavity and the convexity in optimization. We go back to, okay, we go back to, let's introduce a topic, convexity and concavity in optimization. So first I would like to recall what is a strict concave, strict convex functions. Who remembers what's the difference between concave and strictly concave, convex and strictly convex function?
Well, strict concavity or convexity means that it is applied for any variable used, like on the whole graph. For example, if we take a function like the exponent, it is not strictly concave because at the infinity it's like it straightens up, like it becomes like a line. That's why it's not strictly concave. Like I mean,
There's no
like this.
explanation.
I mean, like this.
I have two objections. First objection, it's not exponent. Exponent of x looks like it has.
Oh, I meant log. Maybe.
Okay. Anyway, let's quickly.
Or there's another explanation. So if the second derivative is negative, so it's strictly concave.
Yes, it's sufficient condition to be strictly concave. It's not necessary because we may have it's not necessary condition, but it's sufficient condition to be strictly concave. So let's discuss, let's recall the definition. Okay, I will work with, let's say, convex function. Yeah, convex function is just definition like one definition is, let's say definition one, yeah. The epigraph, so what's above the function, the epigraph of f is a convex function. Convex function, let's add f. The epigraph of the function, epigraph of the function is a convex set. So the epigraph is what is above the function. Or we may have definition 2, so that for every 2 points, so if we consider any 2 points A and B, and any lambda from 0 to 1. So if we consider any 2 points A and B, so let's say that my function is a multivariate function. So A will be in Rn. Yeah. So let's consider 2 points A and B in our multivariate space, and a lambda that is scalar, that is between 0 and 1, then for a convex function, which side should be bigger? The function of lambda times A plus 1 minus lambda times B, or, so it's my question, V, yeah, it's like, I think like V, yeah, or lambda f of A plus 1 minus lambda f of B. Which side, left-hand side or right-hand side, should be greater or equal to the other side? How do you see?
Left-hand side should be bigger.
Yeah, left-hand side is in epigraph, and the right-hand side is the value of the function. So yeah, you are right. It should be like this, less or equal. Yeah, the left-hand side. Yeah. Maybe it's better to stop for a moment and draw once again. So I will use, to not waste a lot of time, I will just annotate my plot. So let me draw the function, and the color will be black. I think that would be better. So I understand that the plot is awful. The formulas are great, but the plot is bad. Okay, anyway, so I have a function. This is my if. Ooh, poor f. I have 2 points. Point A. Oh no, that's awful. Point B. And this is the line that. Oh, sorry, I'm scared of my plotting of the function. And so this is point in between A and B. This is point, let's say, C. And we see that f of C is below. So linear combination of f of A and f of B is higher. So this is the value. So let me draw the vertical axis. And this is the value of the right-hand side. Oh no. Ooh, this is the value of the right-hand side. And this is the value of left-hand side. That's the best I can do. Sorry. Today I've lost my pen. Tomorrow I will either find it or buy a new one. Anyway. Okay. That's the definition of a convex function. Any question?
Thank you. No question.
No, it's clear.
Okay, let's clear this awful plot. Now we can change a little bit this definition to allow for strictly concave, strictly convex function. Okay, this is convex function f. And now we go on to strictly convex function. Oops, definition to B. We need to change the inequality sign. Strictly convex function f. This inequality is strict. If we consider any 2 points, A and B, then the value in a point between A and B should be strictly less than a linear combination of the values of f at A and B. And let's provide some examples. So if I have a function f of x that is the absolute value of x, maybe even 3 absolute value of x minus 5 plus 7. Oh no, that gives me double. Okay, this function, is it strictly concave? Is it concave? Convex?
It's concave and convex, but not strictly.
Strictly concave. Yeah, you are solving faster than I'm typing. Concave, but let's just strictly convex. Yeah, and the answer is that this function is convex and not strictly. Not concave. Okay, yeah, you're right. Let's go on. Now let's check some implications of concavity and convexity.
Excuse
Yeah.
me, can I ask a question about this example? Why is it convex and not strictly convex?
Why it's convex and not strictly convex? So let's discuss. Let me draw this function. Just a moment. So if I draw this function, it's like a module of x, but shifted, translated, I don't care.
Borisovich,
Yeah.
you can enter Desmos and draw it like in a few seconds if you want, if you'd like.
Where?
Desmos.com.
Desmos.com. Okay, I will write Desmos. Okay, I will try it. Okay,
Yeah,
I will try.
click the graphing calculator and that's it. Then you enter the function and it draws it.
Okay. But anyway, I will need to add some additional. Okay, I will try to check next time. So that's roughly how my function looks like. Yeah. If I take point A here, this is my point A. If I take my point B here, if I take, what's happening? I'm drawing. Ooh, yeah, be brave and the face will. Oh, yeah, I managed to do it. Okay, this is the point A and this is the point B. And if I draw a line between the values, I see that if I take any point in between A and B, any point like C, yeah, I really see that the value of a segment is above my function, is strictly above my function, okay?
Yes, and why is this not strictly convex?
But I can choose A and B differently. If I choose A and B line here, A and B, and my segment will just coincide with the function, you see? And the strict inequality that the segment is strictly above my function will not be satisfied. My segment will coincide with the function. And according to the definition of strict convexity, sorry, the segment should be strictly above the function. So if we just look at these two plots, we see that for some values of A and B, the segment is strictly above the function. But for other choice of A and B, the segment just coincides with the function and I have equality sign, okay?
Okay, yeah, perfect. Thank you.
Bada booms. Let's go back. Maybe I should add some words. That means the function is strictly, so how to say it in words. The function is strictly below any segment. So if I would say this equality is this inequality in words, I would say function is strictly below any segment. Okay, but it is not always true for an absolute value of x. Okay, let's move on. What are the implications of convexity and concavity? The same definitions were, I can state the same definitions for concave functions. For concave, the subgraph should be a convex set. For concave functions, I should just reverse the inequality sign. So for a concave function, the function should be equal or greater than segment. And for strictly concave function, I will just reverse the last inequality. Okay, let's move on. What are the implications? So first is implications. Maybe I will add 4 signs. Oops. Implications. First implication that when we work with convex function or concave function, that means that the function is continuous. I will state the theorem only for, let's say, for convex function, but it's also true for concave functions. So if the function is convex on Rn, then it is continuous. Why it's so? Why a convex function needs to be continuous? What's the problem with discontinuous function and convexity or concavity? What's the problem? Why a discontinuous function cannot be convex or concave?
Because there may be a point. For example, like if we see the graph, and then we draw a line, and we know, like for example, let's draw a graph which is convex. We know that it's convex. We know that some function is convex. But then if we draw a line like we drew when we proved that 3 absolute value x minus 5 plus 7 is convex, then we see that there is some point on this interval where our equation does not hold.
Yeah, I agree. Basically, if we have a discontinuity, then basically we can choose a point A and B near this discontinuity, and we can trap. We will not. So if you like, you can prove this theorem honestly. It's not so tough, but I will I will be satisfied just with intuition. So if we select the point A and B, so I will choose the point A a little bit to the left of discontinuity. I will choose the point B a little bit right to the discontinuity of my function, and obviously my segment that links f of A and f of B, it cannot be below the function. It cannot be above the function. So the function can neither be concave, neither convex. Okay, so that's the first implication. If the function is convex, then it is continuous. If the function is discontinuous, we are sure that it's not convex, not non-concave, non-convex. Okay, the first implication is clear.
Yeah.
Okay, let's move on. I need to remove this because otherwise I cannot. Let's clear all drawings. Okay, let's go on. Okay. You always try to speak about derivatives when the function is concave or convex, and you are more or less right. Yes, it's a criterion for some criteria for convexity. Indeed, you are right. If the function f of x is twice differentiable, I'm speaking about multivariate functions, so it's twice differentiable. So f belongs to C2. Yeah, it's twice differentiable. Then you are right. If H will be Hesse matrix, so, let's denote Hesse matrix by just H. Yeah, let's denote Hesse matrix by H, and you are right that if H is negative semi-definite, that means if and only if the function f is of which type? The matrix of second derivatives is negative semi-definite, so it's like the function is like this. So the function is
Concave.
no. Imagine a parabola with negative first coefficient. It's a convex function, yeah?
No, it's concave. And
Sorry, negative semi. Yeah, you are right. Yeah, you are right. Yeah, you are right. Is concave. Okay, H is positive semi-definite. Positive semi-definite, and the function is concave. Yeah, sorry, just I've confused. Yeah, negative means like this parabola with negatives. Okay, yeah. And what about strict concavity or strict convexity? Then implications are one-side implications. So if H is negative definite, and then we can, if H is negative, then the function f is strictly concave, and we have the corresponding statement for positive definite functions. If H is positive definite, then the function f is strictly convex. Okay?
yes.
So for negative semi-definite H, that is sufficient and necessary condition for a function to be concave. And negative definiteness is a sufficient condition, but it's not necessary. We can provide examples when the function f is strictly concave, but h is not always negative definite. Who can provide me an example? So let's find an example. The function is strictly concave, but h is not always negative definite.
X squared plus y squared.
Yeah, you are right. But let's provide something a little bit more. Fine, let's at least y to the power 2020 plus x to the power 42. Let's be a little bit creative. Yeah, this function is strictly concave. Oops, sorry, I need to add minus. So strictly concave. Like that, strictly concave. But if I consider the Hesse matrix will be, let me find the Hesse matrix. It will be like P matrix. I will have what I will have. I will have something like minus 2020 times 19 times y to the power 18. I will have 0. I will have 0. I will have minus 42 times 41 x to the power 40. And the matrix ends here. Yeah. The Hesse matrix will look like this. And I see that if I consider a point x equal to 0, y equal to 0, my matrix will be just 0. In all points except 0, 0, the matrix is negative definite. But at 0, 0, the h, but not at okay.
Okay, all right.
Let's finally go to the link between optimization and concavity convexity. Finally, what we can say about optimization of concave or convex functions. For simplicity, I will work with concave function, but you can clearly state the corresponding statements for convex functions. But anyway, we can formulate some statements for concave functions and formulate corresponding statements for convex functions and vice versa. Just replace maximum by minimum or minus by plus and so on. So I will work with let's work with concave functions because of maximization. I'm just greedy. I like to have plus, maximum, and more. So I will work with concave functions. So let's, oops, not here. Let's work finally the link between optimization and concavity concavity. Okay, so let's imagine that f is a concave function. What else? D will be a convex set. D is in our n-dimensional space. So D will be a convex set. D belongs to D is some subset of Rn. And then we clearly have the first link. Yeah, the first theorem. Yeah, the first theorem. Any local maximum is also a global maximum. Okay? Maybe
Yeah, okay.
To better state the theorem with if then any local, and then it's better to say a theorem like that. If something, then any local maximum of f on D is also a global maximum. Okay? So that's the first link between optimization and concavity. I will only state these results. I will not prove them, but we will use them when we will optimize. So we will use these results. We will not prove them, but if you are strong enough, if you think that your grade is excellent or upper good, then you may try to prove them. This theorem is not too hard. Just apply the definition of concave or convex concave function and convex set. So basically, we will not prove them. We will use these theorems, but if you feel strong enough, then that's not too outside the level of our course. So if you are a very strong student, then that's okay. That's, I think that the proof of this theorem, it's a good exercise for a student who is oriented versus excellent grade. Maybe it's a hard exercise for those who are struggling with pass or fail. Yeah, that may be a tough exercise, but if you feel strong enough, that's okay. That's not too hard. Okay, so that's feasible. Okay, let's move on. Let's state some other theorem. So what is the use of this theorem? If you have a convex set, so that's great. If so, that may be useful on the exam. So if you check that your function is concave and you have found the extrema using, let's say, second order sufficient conditions, or I don't know, graphically, or and then you can just be sure that the local maximum you have found is also a global maximum. That's a great help from concavity. Okay, let's move on. Yeah, we will even add here, second point, the set of maximizers, the set of maximizers, let's call it M. So what do I mean? The set of maximizers, this erg maximum of what's wrong with argmax? Okay, argmax, I'll write like this. Erg maximum of f of x given that x belongs to D. So I maximize with respect to x. Yeah. Okay, the set of all maximizers. So if I find the collection of all maximizers, then this collection is either empty. So there may be no local maxima. That can happen. But if you have local and global maximum, then it's just one connected convex set. So you cannot have for a concave function, you cannot have one maximum here, another maximum there, the third maximum somewhere else. So all maximum points will be in one convex set, is either empty or convex set. Okay, so we have first theorem with two statements. Any local maximum is also a global maximum, and the set of maximizers, so the set of points where the function attains the maximal value, the set of maximizers is either empty or convex set. It may be, you may have many extremas. So let me draw an example. You may have something like, you have a function like and you have a plateau here, and after a horizontal plateau the function decreases. So for these cases the set of maximizers oh, that's awful. Okay. Yeah. This is my function f. And in my case, the set of maximizers, so this is x. I need to, maybe next time I will just use, I will insert Python or R code. And here is a set of, to draw a function. And in my case, this is just the set of maximizers m. So this is set m, the set of all arguments for which the function attains the maximal possible value. Okay, any questions about the first theorem?
I have a question. So
yeah.
What is an example of when we have a local max on a not convex set, but it is not a global max?
Okay, let's provide an example. Just let me look. Yeah, no problem. Let's imagine, so you asked me why D convex is important. Okay, let me provide an example for your question. No, I prefer to have, so that's up to you, but personally I prefer working with step. Okay, so let's provide an example of D. My D will consist of two chunks. So this is my set D. It will be up, and this is will be the second part of D. Okay, my set D is something like from 0 to 1 and from 5 to 6. Okay, my set D consists of two chunks of two segments. Okay.
Yes. Okay.
And my function is like this, just monotonically increasing function. And so believe me, I have two local maxima here. The first local maxima is here is the first local maxima x star. Believe me, it's x star 1, and this is the second local maxima x star 2. Okay, why x2 star is a local and global extremum? Because I can do better if I'm if I should find a maximum on the set D, on the black bold set D, yeah. But x1 star is a local maximum. Why it's local? Because in the neighborhood of x1 star, there are no beta points. I mean, in the set D. Okay.
Yeah, I understand why. Yes.
So the problem is I would like to increase the value of x1 star by moving right a little bit, but my set D is not convex, and so I cannot do so. Why do I need that D is a convex set? I need at least a guarantee that it consists of one piece. So it's necessary condition. And in two-dimensional case, the same thing will happen if you have a non-convex set like a moon. You may have a small extremum on one end of the moon and big extremum on the other end of the moon, yeah. And you would like to go, but it's impossible because the set is non-empty or non-convex. Okay. I mean,
Yes,
like this.
thank you.
And one extreme is here.
Borisich, one question.
Yeah.
Did you call the x2 star the global maximum, or it is?
Yeah, global on D.
On D, right?
Yeah,
Just
yeah,
on D. Okay.
yeah, yeah. Yeah, but we work on D, so we have we are discussing constraint optimization basically. So yeah, we have D set. Okay.
One have question.
Yeah. What's the question?
So is there any other strict rules to make this function happen, or it always happen?
No, I don't understand your question. Could you please type in the chat?
Sorry,
typing.
Sorry, and what happens if our set is also concave and not convex?
There are no concave sets at all.
And so D is our like constraint set. Am I right?
Yeah. So D is a set. D is not a function. F is a function. F is concave, but D is a set. Set cannot be. So there are only convex and non-convex sets. Functions can be concave, non-concave, convex, non-convex, but sets, D is a subset of our space. It's not a function, yeah? D, it's a region in our n-dimensional space.
Yeah, I understand. Thank you.
Sorry, I type it.
Is there any strict rule to let the function happen, or always could happen? Oh, I don't understand how a function can happen. What can happen? A function can happen. I think an earthquake can happen, but the function maybe. So for the moment, I don't understand the question. What should happen? Okay, let's move on. For example, any local maximum is also a global maximum. So we have stated the theorem. Any local, if So we have a precise theorem. We have not proven it, but we have a statement. If f is a concave function, D is a convex set, then any local maximum of f on D will be also a global maximum.
Yeah, thank you.
So that's a theorem. So we
It will be a global maximum on D or on Rn?
No, on D. So.
Oh, yeah, makes sense.
Okay, so let me remove all the drawing. Yeah, we always work on some constraint set. Yeah, on D. On D of f. Of the same function on the same set. Yeah. Okay, let's move on. What will we have, let's say, 15 minutes. Okay, so let's move on to a very to the logic of Lagrange multipliers and so on. So the theorem 1 is useful, but let's move on to the theorem 2. Theorem 2, basically it's a consequence of a theorem 1 that if f is a concave function, if what do we need to have concave? It should be differentiable. Yeah. We now work with first derivative. F is a differentiable function. Differentiable function. So f belongs to C1. Yeah, it is differentiable at least once. Okay. Then basically first order conditions for unconstrained optimization. Yeah. Let us add once again for just a moment. D will be convex open set. Yeah, it will be convex open set. Then first order conditions are sufficient. So what do I mean? I mean that the conditions that gradient of f is equal to 0 at some point is necessary and sufficient for x star. Yeah, gradient of f of x is 0 is necessary and sufficient for x star to be local and global maximum of f on D. Okay, the second theorem is clear. So if we add a little bit to the first theorem, so what is added? Now D is not only convex, but it is also open set. Okay, f is concave and differentiable function on D, and then bingo, first order conditions are sufficient. So what does it mean that first order conditions are sufficient? That means you just check that the first derivative is 0, and you say, "Woo, I have found a global maximum." Yeah.
Well, that only works for unconstrained optimization.
Yeah, for the moment, you are right that we will provide the next theorem. The next theorem will be for inequality constraints, but be careful. Generally, you're right that the theorem 2 applies to unconstrained optimization, or it is also applicable. Be careful, because I have not specified what is D, just a mild requirement that D is convex open set. So if I consider a problem like that, let's x 5 minus x squared minus y squared. For example, I need to maximize, yeah, and my condition is my set D is described by x plus y is less than 10, strictly less than 10, then it's okay. Because my function is concave, my function is differentiable, and my set D, it's a half plane, so it's convex, half plane, it's an open set, and basically that's all. It's an open set, it's convex set, and as my inequality constraint is strict, then this theorem 2 is applicable. Okay?
Thank you. It's okay.
So if I will find the point on my set D that satisfies the condition gradient, all derivatives are equal to 0, then bingo. This point is certainly a maximizer of my function. Okay?
Okay.
Okay, so on D, yeah, we always work on D, yeah. On concave function, I should add on D, differentiable function on D. I don't care what happens outside D, because everything is on D, on D, on D. Example, theorem is applicable to the case because this is a half plane, convex and open.
Sorry, would you please remember what the open set means?
Open set means the set does not include its borderline.
Ah, yeah, thank you.
So we have a formal definition that every point is contained with epsilon neighborhood, but intuitively an open set is a set that does not contain at all its borderline.
Yeah, okay, thank you.
Okay, and now finally for inequality constraint that may be strict or non-strict. So finally, the main goal of current lecture, theorem, let's say 3. It has even a name, Slater's. It has even a name, Slater's condition. Okay, so now let me provide the setup. So let's consider maximization problem. So what should I write? Okay, so my function f is concave, differentiable. So u will be some open convex subset of Rn. I will have inequality constraints H1, H2, and so on. Let's say, I don't know, L. This will be constraints, constraint functions. And they should be also concave. Concave functions. What else do I need? I have specified UF. My D is U intersection with, I know I will write like this, all points X such that H1 of X is greater than 0, H2 of X is greater than 0, HL of X is greater than 0, and X belongs to U. Okay, this is my set D. So F is my goal function. I would like to maximize it. U is some open subset given by strict inequalities. H1, H2, HL will be non-strict inequalities. And so my problem is to maximize F. So we are considering this problem subject to X in U. H of X is all H of X are greater than 0. So we have the following problem. The problem is to maximize F given that all H1, H2, H3, and so on are greater or equal than 0. Okay, the problem is clear. The requirements are clear. F is a concave differentiable function. U is open convex subset of Rn, probably given by strict inequalities. H1, H2, HL are functions that are concave and that are used as constraints. Okay, the setup is clear.
Excuse me, could you give me an example about this status condition? For example, just a real example.
Yeah, we have not finished yet. We haven't finished yet. Just the setup. F is concave, U is open convex, H1, H2, HL are concave function. Every term is clear or not? Okay, I hope that you have no questions. Finally, Slater's conditions. Slater's condition. There is a point. There is at least one point. Let's call it bar X in D, such that at this point H1 of this special point bar X is strictly greater than 0. H2 of this special point bar X is strictly greater than 0, and so on. It's not an average like in statistics, it's just a point in Rn. So do not confuse this notation with arithmetic mean. So there is at least one point such that at this point, every h, h1, h2, h3, and so on are strictly greater than 0. If then, okay, if part is very long, but now the then part is very easy. I will say it in words first, and then maybe we will provide some examples. Then complete happiness, the bingo complete. So let's write that we have then we are in a paradise. Then we are in a paradise. No need to check IndiceQ. No need to check second order conditions. We are just happy. First order conditions are necessary and sufficient. First order conditions. So we have stated them. There is a big long list of first order conditions. So with non-negative constraint on lambdas and so on. So a long list with lambda I is greater than 0, lambda I times partial L partial lambda I equal to 0 is necessary and sufficient. Okay, any questions about theorem number 3, about Slater's condition? We have a concave function, open convex subset, concave functions used as inequality constraints. We need to maximize f subject to these constraints and maybe some additional open set constraint u. And we have a special Slater condition. So maybe it's better to make it in bold. We have one more special condition. There is at least one point x bar such that at this point all functions are strictly positive. And then we are in a paradise. Don't check IndiceQ. Don't check second order conditions. Just write the Lagrangian function. Just write first order conditions. Solve these equations. And bingo, you have a global maximum. Okay?
Okay.
So let's provide a small example when this Slater condition is when this condition is satisfied. So let's provide an example. My goal is to maximize 5 minus x squared minus 6y squared, or maybe y cube, yeah, or maybe y to the power 4. Okay, that is my on R2. Given that, and I'll give you some inequality constraints. My inequality constraints will be what it will be. My inequality constraints will be x squared plus y squared is less than 100, and 6x plus 2y is less or equal to greater or equal than -5. Okay. So let's check whether Slater's conditions, whether this theorem is applicable. Okay, first, is my function f concave? Yeah, both derivatives are negative, so it's concave. Yeah. So the first condition that my function is concave and differentiable is satisfied. So my U here open subset of Rn. So I work on R2. R2 is an open subset of R2, obviously. Okay, what are my H1 and H2 in this problem? In this problem, my function H1 is just 100 minus x squared minus y squared and is concave. Concave. My function H2 is 6x plus 2y plus 5. It's a linear function, and so it's also concave. Now, can we find the function? Can we find a special point x bar? Any point is okay. Just a random guess. Any point is okay. Just you need to check that you have a point in which all constraints are strictly greater than 0. Okay, who can provide me a point in which all constraints are non-active but satisfied?
0, 0.
Yeah, bingo, 0, 0. As bar x, we can choose 0, 0. We can choose 0, 0. Indeed, you are right. Because if you plug in 0, 0 in H1, you will get that H1 of 0, 0 is greater than 0. If you consider H2 of 0, 0, it's greater than 0. Bingo, all constraints are satisfied. So if I'd like to solve this optimization problem using Lagrangian function, I just write Lagrangian function. I just write for all first order conditions. We have written them 3 lectures. So first order conditions do not change. They are the same. But do not forget that as we have inequality constraints, then lambdas should be non-negative and lambda times dl d lambda should be 0. So I just write first order conditions. I just solve them. I don't care about in DCQ. I don't care about second order conditions. I have solved my problem, and that is according to the first theorem. Yeah, according to the first theorem, I have f concave, d convex. It's also global, local. So bingo, we are in a paradise. We have found global extremum, local extremum. We have not checked. We have not checked in DCQ. We haven't checked second order conditions. Bingo, we save a lot of time, and we find global and local maximum. Okay.
Yeah, I'm sorry. I have one question. And can you understand somehow this theorem intuitively instead of simply remembering the conditions?
Basically, it's better. So our lecture is finished, but the problem.
Да, может быть, может тогда на русском.
The problem is maybe we will discuss some counterexample next time to this theorem when, so to develop intuition, you need to just try to construct an example where this condition, Slater's condition, is violated and there are no such point. And when you look at some examples, you really see why it's needed in this theorem. So the good exercise for you is try to find a function for which the Slater's condition is violated, and for which the first order condition in Lagrangian function is not sufficient. And we will discuss, I think, 2 or 3 examples for this Slater's condition next time. So that's a good question, why we need such a point x bar. Yeah, that's a good question. I agree. Try to answer it. And then we will discuss 2, I think, examples. That's sufficient.
Понятно, спасибо.
Just a question of how it's better with beautiful equations in Colab or with handwritten notes. Who votes for which version?
Actually, for me, both versions is okay, but this one is better.
So just write it in the chat because I understand that today it was like the only solution, because I've lost temporarily my pen to write on a tab. But next time I certainly will find it, or I will buy a new one, and just say your preference.
Boris, I think that handwritten notes are much more efficient.
Okay, just write it in the chat. I will.
In the chat. Okay.
So, okay, but thanks for your comment. Yeah. So we have finished. The link, I will not remove it, so you can just copy the link from the Zoom chat. So yeah, and the text will be okay. And you may, maybe one more advice, maybe it's a good advice to recall that the best book on optimization at our level is Rangaranjan Sundaram. Sundaram is the best book. So just it's I don't remember the title. It's first course in optimization. It's very well written. There are some misprints, but in any book you may find misprints. Sundaram, first course in optimization. Okay, I will collect the votes, and maybe if okay, but state your preference. I will try to take them into account. Okay, thank you. We have done everything. See you next time. Have a nice evening.
See you. Thank you.
Thank you very much. Have a nice weekend.
Thank you very much. Bye.
Thank you. Goodbye.
Bye-bye.
Actually, Professor, it seems looks like the balance for electric version and handwritten version is same, and the other students say it's indifferent.
Yeah, I will look and I will count how many students are for that or that version. Yeah, I will.
Yeah, actually, my opinion is, I mean, if handwritten or electric version, which one you like is my option, because for me everything is okay. But if I have to choose one, I like this Python version. Yeah.
Okay. Thank you. Bye-bye.
Bye-bye.